We have just built the joint density, a surface over the plane whose volume above a region is probability, with marginals found by integrating one variable out. This video slices that surface, because that is how observation works in the continuous world. You learn something, and the whole model updates. We condition a density on an event and truncate and rescale returns in smooth form, then condition on an exact value, an event of probability 0, and make honest sense of it, average the slices to get conditional expectation, and let it estimate a signal through noise, and close by transforming pairs with the Jacobian formula. Chapter 4's ratio has served every kind of conditioning so far, and it crosses into the continuous world untouched. Given an event A with positive probability, the conditional CDF of X is the probability that X is at most X, and A happens over the probability of A. Differentiate, and the slope is a genuine density, the conditional PDF of X given A. Nothing new is postulated here. The ratio we trust meets the CDF we trust. The case to internalize is conditioning on an interval. Suppose a component's lifetime is exponential and we learn it failed within the first 2 years. Outside the interval, the density dies. Those lifetimes are ruled out. Inside, the shape is untouched. Every value divides by the same number, the probability of landing in the interval, and the curve rises just enough to enclose area 1. Truncate and rescale, the move we ran on the geometric bars in Chapter 7, now on a smooth curve. And the event need not involve X alone. Condition 2 exponential arrivals on Y at most X, and integrating the joint density over a triangle hands back a clean conditional density for X. Any region of the plane can play the role of A. Now the harder question, and the one observation actually asks, a receiver reads Y equals exactly 1.3, but for a continuous Y, that event has probability 0, and dividing by 0 is not conditioning. Escape by a limit. Ask instead that X land within a small window delta X, given that Y landed within a small window delta Y. That ratio is honest. Both windows have positive probability. The joint density times both widths over the marginal times delta Y. The delta Y cancels. What survives is the definition. The conditional density of X given Y equals Y is the joint density along the slice divided by the marginal of Y at Y, defined wherever that marginal is positive, integrated over a set, and you have the conditional probability that X lands there. Picture it on last video's surface. Cut across the support at height Y, and the profile of the cut, renormalized to area 1, is the conditional density. Try it on the uniform disk. Given Y equals 1/2, the slice is a chord running from minus root 3 over 2 to plus root 3 over 2, and the marginal there is root 3 over pi. Dividing leaves a constant, 1 over root 3 along the chord. A flat surface conditions to a flat slice, uniform in, uniform out. Each observation hands us a fresh density, and any density has a mean. The conditional expectation of g of y, given x equals x, is an integral now, g of y, weighted by the conditional density of the slice. Given an event, the same formula runs with the event condition density. Chapter 7's discovery returns intact. Sweep the observation, and the slice means trace a function h of x. Feed the random x in, and the conditional expectation of y given x is itself a random variable. Here is that machine doing engineering. A transmitter sends a standard Gaussian signal x. The channel adds independent standard Gaussian noise n, and the receiver reads y equals x plus n. Given the value received, what should it guess for x? Slice the joint Gaussian surface at the received y. The algebra collapses to a Gaussian in x with mean y over 2 and variance 1/2. The minimum mean square error estimate is the mean of that slice. The estimate of x is y over 2. Split the difference between the received value and the 0 mean prior. That estimator, a conditional expectation, is the workhorse of communication and control. One tool remains, transforming pairs. Chapter 9, turn the density of x into the density of g of x, paying with the derivative of g. Now map two variables to 2. y1 and y2 are functions of x1 and x2, differentiable and invertible, so every output point comes from exactly one input point. Watch a small square of probability. The map carries it to a parallelogram, and the factor by which its area stretches is the Jacobian determinant. the determinant of the 2 by 2 matrix of partial derivatives. Probability itself cannot stretch, so the density must compensate. The joint density of the new pair is the old density at the pre-image divided by the absolute Jacobian. One dimension paid with the absolute derivative of g. Two dimensions pay with a determinant. The star application takes one breath. Push a jointly Gaussian vector through any invertible affine map, ax plus b, and the Jacobian formula returns the Gaussian form, mean am plus b, covariance a sigma a transpose. Gaussians survive every affine map in any dimension, which partly explains why they dominate engineering. The key idea of this video, conditioning a density, is slicing and renormalizing, and every slice has a mean, which is the conditional expectation.